So actually, I think my title is a different one, and it will come up in the third slide, I guess, because I wanted to link with Dan Rigden's great talk on the overview of how prediction methods are performing right now, really this advance is one of the most striking of the last decades, and it's a game-changing algorithm that has allowed to harness knowledge that we had and that people have been trying to use for years to predict accurately structures and to relate the information we had on all the experimental structures and the evolutionary conservation. So that we could, and I like to draw attention to this attention paper, which was very well game changing, and that allows us to translate say English into Spanish by realizing that when you have a sentence like the cat did not cross the street because it was raining, it doesn't refer to cat or to street, but actually to it being raining, and that in Spanish, for instance, is completely unnecessary. So this, we've been able to translate sequence into structure. But actually, this will open so many other possibilities and will go so much beyond this point in the next years when we are able to translate sequence into function, which, going back to the language analogy, it would be a bit like translating words into meaning. So if an English colleague said to this, oh, that's a very interesting idea, before living in the UK, I would have translated it as its face value, but now I know better, and I know that the Spanish translation would be closer to menuda tontería than to que interesante, or it would be what the German called the Schnapsidee. So what will be after in the next years will be surely not just translating words from one language into another, or getting structures from their amino acid composition, but knowing about the chemistry from this same information. And well, to explore things in this direction, we are developing Archimboldo Air to, and I think my title was more like prediction-based tools to plan and interpret experiments with AlphaFold. Anyway, I would like to mention for one slide also that one of the things that worries me is that in crystallography, what is our outcome? Is it a model, or is it the experimental determination of what we have in the experiment? Because we still have a phase problem and a long tradition of balancing experimental data and prior knowledge, which was rather equilibrated, but at the moment we are enforcing model everywhere at every possible step. And I think that the question is frequently shifted into what is the best model, when we shouldn't lose track of what is the experiment telling us, what do we have, not how canonically, modelly should our experiment, to our structure be, the outcome be. So chiming into the crafty crystallographers initiative, I had programmed a small animation. This is a line drawing of a colibri, and it's decomposed into a Fourier series because it's converted into a scalable vector graphics, which is a description of a path. So what we have here is a function of time, and taking samples along the path in time, and it's represented on a complex plane, so the usual real on the x-axis and imaginary on the y-axis, and you see all these little circles corresponding to the structure factors that are being added with the corresponding frequencies and with the corresponding phase shifts. Yeah, and here we are reconstructing the image of this colibri. And now, yesterday in Graham's talk, there was well, a very thorough analysis of errors and well, how to get the best possible analysis of data, and also the other talks in the session. But our Fourier approximation would only be exact with infinite terms, and that's in the absence of errors. So we see when we only have lower resolution terms, the 0 term, which is giving us the center of coordinates and the center of gravity of the image, we have an egg very properly for the colibri. And as we start adding terms, so increasing our resolution, we will be getting a better and better approximation. And we are very used to thinking in terms of when we have low resolution, there are things we don't see. And you see, the image is getting closer to the colibri. The amplitudes and the phases are perfect. I calculated them from the colibri I drew. So it's just that there are no errors, some are missing. And you see, we are missing part of the beak, but we are also seeing parts that are not there. So it's not just a matter of missing features. We have features that here, for instance, what do we have here? Well, a peptide ligand? No, actually just an artifact from our resolution being low. It's not there. It's only when the number of terms will increase that approximation gets better and this artifact will disappear. So for low resolution, and given also the given the way in which models dominate our structure determination all over, we might want to accept not just that the data can't complain about the model we are giving them, but that they can discriminate between it and something different, to accept that our determination is experimental. Otherwise, it's a model and it may be very useful, but it's not an experiment if our experimental data can't prove something. Anyway, for the effect of errors and so, I display this on our web. Going back to the subject, which is a bit schizophrenic because on the other hand, this model prediction is so exciting and there's so many things one would like to look at that, well, the rest of the talk would be about that and not about accurate experiments. But people have been looking at interactions the moment it came out, and so it's also building on this work, taking duplicating sequences with linkers to model multimers, and of course, whatever you try to predict should have some, you could predict irrelevant things if your base assumptions are completely off. And there's also this interesting work on conformations of transporters for different functional states. And Dan was also referring to tools in Collab for that. So changing the shallowness of the alignments allows to obtain broader representation of the different states. And that's the observation the authors of this paper were doing. But ideally, we wouldn't want to get a lot of sampling. We would want to have all of them and maybe direct what we have. So for this, can we draw a particular state? We would need to analyze the beginning information for an AlphaFold search. And to this effect, we are using our characteristic vectors in ALEPH and their distribution, which gives us matrices with properties like distances and angles characterizing the polypeptide geometry. And we can compare them. We can compare the matrices with Frobenius distance because they are forced into the metric of the query sequence. So everything goes anyway into a common matrix, which is the features PKL, because whatever is not in your sequence can't be, even if it exists outside of your sequence in other sequences or in other templates, won't be fitting there. And if something is missing, it's missing. So you have all matrices of the same dimensions, even if part of them might be empty. And also using what Greta Assmann was describing yesterday in her talk about pairwise correlation between different metrics, which is work Kai Diedrichs is doing. So we can partition this information and select templates one direction or another to push AlphaFold towards the desired states. And that's what the matrices look like. They can show us where changes are in case there are, well, if changes are low and where they occur, or if differences are much broader, and also nail down where the differences are here, for instance, in this helix, in the lighter parts of the matrix. So that's what we are using. And for instance, for the case of this family of transporters, which is one of the 7 in the paper of the Alamo paper. And if we retrieve the templates from AlphaFold and cluster them for their geometries, that's reduced to a case of 5, we can see which are, or we can automatically derive which are closer geometrically and group them and separate the prediction in different ones and point it towards the substrate-free state for those ones and the amino acid bound state for those ones. And that's what our output looks like. It would give us the better prediction, and we can modify the sequence. Modifying the sequence of templates is a way of enforcing more or less the information that one is providing through that template. Like identical sequence would be much higher weighted. And this is the analysis from the Frobenius distances and the conclusions. Those are in the same way because they are really equivalent, and they and we use energy to assess also interactions and interfaces that are formed. And in this case, we have 2 equivalent predictions favoring mostly one of the templates that we were giving it. So we've also been looking into conformations in the case of multimers that are rather asymmetric. These LTTRs are the most numerous family of bacterial transcriptional regulators. They are typically tetramers, and they show, or they are expected to show, large conformational changes upon binding of their substrate and DNA to initiate transcription, or actually they also repress it. And even containing 4 copies of the same sequence, you see that it tends to adopt 2 extremely different conformations. Whereas a multimer search would typically give you a symmetrical representation with all the copies equivalent, because there's maybe 15 different non-unique structures of other transcription regulators. They share a relatively low homology in the so the closest are TSAR and CBNR to ours, which share an homology of an identity of 23 and 22%, and others are more distant, but also the structures are differing very much. And well, this could be due to sequence being different, or this could be due to their representing different snapshots of a mechanism, and possibly both factors play a role. So what we were doing was predicting them in versions of the one that we had just determined experimentally. It is that are following in homology out to all the other templates available, and analyzing the changes they have and towards the experimental structure and towards their templates through the changes in the interfaces, and using the energy evaluation to decide whether what comes out has any plausibility or would be impossible in that form. So one thing that was reassuring is that in all cases, and this minimal information given, the dimer forfeited C-terminal domain was closer to the experimental structure than to any of the other templates that we were giving it. And also, whereas we got relatively close TSAR-like version of ATZR, 23% identity, I remind. So with the same kind of interactions and main chain interaction between the dimers forming the interfaces, and the main differences in the part where the ligand is bound in our experimental structure. There was no way to persuade this sequence to adopt the structure like the template of CBNR, which is 22% identical. So practically the same as TSAR, not just because it wasn't forming this interface in the middle. We know it forms a different one, but also not building a main chain interaction for the C-terminal domains. So we had hypothesized whether rocking mechanism of the C-terminal domains would play a role. There's no, it might, but there's no way to persuade ATZR to adopt the open way, or there's no way to persuade CBNR to adopt the closed extension of the beta sheet from any of the others. And sequence of the templates we are giving, I had mentioned it before, plays a role, and you can modulate how the information is weighted by giving it a polyala or the original sequence, or changing it to the target sequence, in which case nothing will move if you, or it's staying very much as in the template, whereas it adapts if you give it polyala. And with that, I would like to finish and acknowledge my wonderful group and that has participated in this work, and also the funders, and collaborators, particularly Kai Diedrichs from Constance and Massimo Samito, who is working at AstraZeneca, the taxpayers providing the funding for our projects, and CCP4 that has been funding us for the last 3 years. But especially, I would like to thank George Sheldrick, because, well, yesterday when Meta Landa was giving her wonderful talk and mentioning the difficulties she had to establish herself and her research, it reminded me of this paragraph which I reproduced, because it's, to me, the highest insight I've got on this problem. So whoever looks different of the preconceived idea someone has for a role gets less opportunities and needs to fight for opportunities, whereas people more conforming to the general image will get opportunities literally laid at their feet. And so my biggest thanks go to George Sheldrick for giving me the opportunity to do an habilitation, and which I completed in the 21st century, not talking about the 19th century. And so good result for year 2023 should be to support more emergent groups and look beyond what is the typical image of someone in those circumstances. And I'd like to say that University of Göttingen is thinking of giving some funding a prize at the ECA with some of the Shell-X industry fees for people having done great contributions but not holding a permanent position. So emergent PIs. Thank you.